And so now that we've kind of covered, the basics of differential equations in terms of the definitions and different classifications, and then did a refresh on implicit differentiation, let's actually start, solving some problems now. So we'll begin with, this section, and I'll go over all of them just for, full clearance of this because these are, pretty easy to do. So we're asked to state the order of the given ordinary differential equation and then determine whether the equation is linear or nonlinear by matching it with 6. And that, of course, is just the that's just referring to the definition of a linear nonlinear ordinary differential equation. So if we look at 1 here, we have 1 minus x y prime minus 4x y prime plus 5y equals cosine x. So let's kind of actually analyze this a little bit better, right? So we can take this and kind of put it in here. So let's kind of take a look at this and see what's going on, right? So we have, the 1 minus x y prime. So let's analyze this, right? Well, we have the 1 minus x here multiplied by the y prime. So so really all you're asking, right, is this scaling off of just, off of just the derivative, the second derivative of y here? And is that being scaled with, another factor in terms of y? And we know 1 minus x is not in terms of y, it's in terms of x. So we can say that, no, this part is safe, it's linear. So moving on to the next part, the next contribution, where we have negative 4xy prime, right? So again, we ask the same question. Is this scaling off of just y? And we see that it's scaling off of just y here because we have negative 4x. So this also is good. We can say that that part is linear. And then we move on to the 5y. Again, we're just looking here at a constant and a factor in terms of y. So we can say that this is linear. It's good. So the whole left side is linear thus far. And then we look at the right side. It's the cosine function in terms of x. So we can say, again, that this is linear right here in terms of y. So the whole equation there. And then, of course, we have to look at the highest order of the derivative. We see that the highest order is 2, so we would say that this is a second order linear differential equation in terms of y. And if we look at the answer, we get that exactly right. So moving on to number 2, we have the same form here, but a little bit different. We're using the Leibniz notation, but don't be fooled by that. It is still, the same general principles going on here. So we look at x d3 over dx to the third. So again, we're just asking a simple question here. This is a derivative in terms of y. Is the y being scaled off of itself, right? Is this here a factor in terms of y? And we see that it's in terms of x. So we can say that no, this part is perfectly fine, right? And again, we move on to the next part. And it's really just as simple as, moving through each one, seeing, and then judging it according to, the definitions that we have. So we have here dy over dx. This is a first order derivative here, but it's being raised to the 4th power. And again, what are we looking for? We're looking to see if y is being scaled off of itself or raised to, past the 1st power. And we see that since this derivative, you can think of it as this, right? Since this derivative is being raised to the 4th power, this does violate the just general linearity. So it is nonlinear. And so we're done here. We see that the highest derivative order is 3. So we can say that this equation is a 3rd order nonlinear differential equation, and we're done. So we move on to number 3, and again, we'll just take this here and abduct that, and then we take a look at this. So we see that this isn't in terms of x and y, it's in terms of t and y, but that still doesn't really change what we're doing here, right? We're still just analyzing this in terms of t, in terms of y. In this case, we're analyzing this differential equation in terms of y. So we can take a look. You'll see immediately that the highest order actually is 4. So this is a 4th order differential equation, right? And then we just, again, move through the terms. Is y being scaled off of just itself? Yep, we see that this is the 4th derivative and it's being multiplied by t to the 5th power. So that part's fine. First part's fine. And then we move on to negative t to the 3rd times y, or the second derivative of y, or y prime prime. Again, y is just being scaled off of t again. So that part's fine. And then we have 6y, it's just being scaled off the constant 6. So that's fine. So we say that this is a 4th order linear differential equation. And then if we open this up, linear 4th order. And again, we're just moving through the rest of them. We'll cover them all, just to, again, fully kind of go through. But I think at this point, we don't even need to, do it term by term and show you in the Excel draw. So we'll just kind of go through it here. So we see that, again, we're looking for, even though it's different variables, again, all we care about is the order of the derivatives and the linearity, right? So we see that this is a second order derivative of u with respect to r. So this is fine here. This is linear in terms of u. That's what we're looking for. This here, linear in terms of u. This here, linear in terms of u. But when we get to here, cosine r plus u, right? Because the cosine function is utilizing the u value, this is no longer linear, right, in terms of u. And you could even fully expand this using the sum angle identity, and this would give you cosine r times, cosine u. And because we have the cosine u being used, and then, the other side is minus sine r sine u, again, sine u is being used, since, you don't want this u ever appearing inside a cosine or a sine or any transcendental function. We can say that this violates the linearity, and this whole thing, of course, would now just be a second order nonlinear differential equation. So moving on to 5, of course, we have a differential equation of y with respect to x. So this is the second derivative, so we know immediately that this is a second order differential equation. And then we look over here on the right side, so it's a square root, that's fine. 1 plus dy dx, so this is, you can think of this as y prime, but because the y prime is being raised to the second power, then we can see, of course, that this is already in violation. So this is, nonlinear, second order nonlinear. And I think, another thing that might come to mind, you look at this and you say, well, what if the 2 wasn't there, right? What if it was just 1 plus dy dx all square rooted, right? And because of the square root, actually, because, the 1 plus is under that square root, then we would actually say that that also does violate the linearity. And so moving on to, 6, we have, again, capital R with differentiated with respect to t. So this is a second order, as you can see. And then we have some constant k to the negative, or rather a negative constant k over r squared. And because r is being raised to the second power, or rather it's being raised to the negative 2 power, actually you could say more like, since you imagine this as just being r to the negative 2, then this also does violate linearity. So this is a nonlinear second order differential equation in terms of r. And then moving on to number 7 here, we just look at this, we see that this is a third order differential equation, but then we look, and again, we see that y is just being multiplied by something other than y. So this is fine. This is perfectly linear. So we can say that this is a third order linear differential equation. And then we reveal that there, and we get the correct answer. And then for number 8, of course, we have x minus 1 minus x squared over 3 times x plus x equals 0, right? And then you'll notice actually that this here, it's a little bit hard to see. So I'll zoom in a little bit. You can see that we're actually using dot notation here. And so because of that, we know that x is the differentiated variable. We see that x, of course, is being raised to second power here. So, and also, of course, it's being multiplied by its derivative here. You see that this first derivative, they're being multiplied by itself. So that obviously violates linearity. So this, we would say, is a second order nonlinear differential equation. And so moving on to questions 9 and 10, right? These are a little bit more of the same, but a little bit more in depth, right? So we'll analyze this to see, we're already told our first order differential equations, and now we're analyzing them for the indicated dependent variable, and then seeing with respect to that variable whether or not it's linear or not, kind of seeing the linearity of that. So if we look at this in terms of y, right, we'll look at it in terms of y first. So we see already that we have, the problem here of y squared, that kind of already violates, the linearity, even though, of course, that we have, the derivative of y here, just perfectly fine right here. Because of this being raised to the second power, of course, this is nonlinear in terms of y. And then if we look in terms of x, of course, we see that x is perfectly fine. It's just being multiplied by, a factor in terms of y. And over here, we have x multiplied by the derivative of y. So that is perfectly fine in terms of x. So we would say that this is nonlinear in terms of y, and it's linear in terms of x. And if we look at the answer here, we'll see linear in x, but nonlinear in y. And then same thing with problem 10, we see that we have u dv plus v plus uv minus ue to the u, du equals 0. And so if we analyze it in terms of v, right, well, if we look through here, we have the derivative of v times u, so that's fine. Then we have this kind of quadratic almost in terms of u and v. And then we see, well, v here is fine. U is again being multiplied by v here, so that's fine. Then we have this just in terms of u times e to the u, the exponential function right there, and then du. So as far as in terms of v, like this is perfectly fine. So we said that this is linear in terms of v, but then of course going to in terms of u, we see that, you know, this right here already is a big problem. And then of course when you add to the fact that this is actually being multiplied by du, then of course we would say that this is nonlinear in terms of u. It's really as simple as that.